Okay, folks. I guess last time we looked at nodal analysis and basically used the idea of Kirchhoff's current laws and added up currents flowing into a node. So this time we want to look a bit more at Kirchhoff's voltage rules and look at the voltages or the voltage changes as we go around a loop or in a mesh part of a circuit. And I guess we'll introduce the concept and how we actually do some problems, and then I've got a couple of examples to walk through with you in terms of how this works. So today we want to talk about loop analysis. Sometimes called mesh analysis, basically the same topic. So the best way to start is let's think of a circuit. And we're going to draw a circuit that's got a bunch of components in, so we'll have a current source. And a resistor, another connection. Okay, so one of these square window frame-like structures with a bunch of resistors. We've got a current source, and we've got two voltage sources connected together. And we can make some terms, so we can apply some numbers here. We can call this I of A. I think the book in this one actually uses T because the current may change as a function of time. We'll call this R1, R2, R3, R4, and R5. So 5 resistors connected together, and then 2 other voltage sources. This one is called V1, function of time, and this one, V2, is a function of time. So an independent current source, we know this is always going to deliver the same current. These are always going to deliver the same voltages, and we've got a bunch of resistors and some current flowing around that circuit. So loop analysis is really what we call KVL, Kirchhoff's voltage law. I remember what that said? Sum of the voltages around a loop, any closed loop, equals to 0. And in this circuit, the way we define, there's a number of ways of defining loops. But we could look at perhaps this loop here. And I find it useful to draw a clockwise current within a loop. So the orange arrow is the current flowing in that loop. And let's call that current I subscript A as a function of time. And for the other loops in the circuit, I can go around and I can make the same definition. I can say, well, in this second loop, there'll be a current flowing. And it'll be in that sense. And we'll call this I B. And we'll keep the convention of some time. We'll call this one I of C as a function of time, and this one I of D as a function of time. So we call these the loop currents, or I guess mesh currents perhaps. But they're local current flowing in each of these loops. But drawing them this way, we can begin to notice some things that help us with the circuit. So we know what I of A is. That's the current flowing around this loop. So it has to be the current flowing through this branch. And we know the current flowing through this branch. It's I of 1, it's the current source, because we know this always delivers the same current. So I of A we know straight away. We know the current flowing through resistor R1. Well, if I go with this current, it's going to be I of A flowing in one direction, and if I look closely, I of B is flowing in the other direction. So the total current through that resistor is going to be the sum of those loop currents. It's going to be I of A minus I of B. Likewise, I know the current flowing through R2. There's only one current, so if I know I of B, that flows through that current, that loop. So you can begin to say that if I walk around these circuits and look at the voltage changes, I could begin to work out the various currents. I could see from this example, maybe I get 4 independent equations. Each loop is going to give me some equation. Those equations may end up being the same or different, but I could solve those equations, system of perhaps 4 equations, and that might give me enough of the unknowns that allow me to work out all the voltages and the currents flowing in the circuit. If we look a bit further at the circuit, we can look at trying to identify the nodes. Nodes will take us the broadest sense as when 2 components join together. So we could certainly say there's a node up here, because I've got 1, 2, 3 components. I don't really think this is a node because it's not connecting to another component. So let's just look at the points where multiple components connect together. Certainly a node here, a node here, node here, a node here. So I could say on this there are 5 nodes. We could also identify a number of branches in this circuit, and that would be, remember what a branch was? Part of the circuit that contains a component. So I know there's 5 resistors, 2 voltage sources, 1 current source, so there must be 8 branches in this circuit. So there'll be 8 branches. And it turns out, more as a sort of ready reckoner for you, that the number of independent equations you can figure out for a particular circuit, you can define as, if you know the number of branches and the number of nodes. So the number of independent equations is given by number of branches, so it equals branches minus nodes plus 1. 8 minus 5 is 3 plus 1 is 4, so we've ended up with 4 equations. So that would give us 4 in the example we've got here. So it looks like we've identified them all with those loop currents. But you also might say, well, didn't you previously say that if I take a loop right around the outside of this circuit, that's also a valid loop? It doesn't cross a node more than once. And sure, I could come up with another equation. Excuse me. But it turns out I don't learn any more about the circuit. It basically replicates what I already know with those loops. Maybe it is easier to take the outside loop, or maybe I can take a loop around 2 of these. So again, there are a number of different ways of dividing up the circuit. So that's what we mean by loop analysis. This is a sort of rough and ready reckoner to make sure that you are in the realms of being able to solve the circuit. Maybe what makes more sense is if we try and do some examples, or try and do a few examples. So let's write down what we know about this. So I guess we can look at loop 1. And for loop 1, when I've got a current source in the loop, I'm given the current, so I know what I of A is. What have I done wrong? Yeah, so that's it's Monday, so we're off to a slow start. So let's try that one again. So let's just call this current I, or I of 1. That's what I'm confusing you with. We'll denote this current flow, denote this current flowing in the loop, I of A. So that tells me that I of A, the loop current, is equal to I of 1, the current provided by the source. I could also say, well, I need to know the real current in this resistor. Maybe I've got another color here. So what's the real current flowing down this branch? And let's call that I of 2. So the two loop currents I've generated, one flows in the same direction, one flows in the opposite direction. So from this, I get that I of 2, the real current flowing in the loop, is going to be I of A as a function of t minus I of B, function of t. So I of A is supplied by this source, so I know that value. I of B I don't know yet. It's going to depend on the rest of the current. But I know the real current flowing through that branch now. It's going to be this one minus this one. I could say that maybe this is I of 3. And remember, we're interested in the current flowing through a single branch, because if we know the current flowing through that branch, and I know the resistance, I know the voltage. Question? Why isn't it IB minus IA? So I2 is going this direction. I of A is going the same direction. I of B is going the opposite direction. So the value of this current must be this one minus the one that's going in the other direction. So if I remember, if I get a negative number, it means the current is flowing in the opposite direction. So I can define these fictitious loop currents. And these are the loop currents that balance up the voltage drops around the loop. They're not the actual currents flowing around the loops. The actual currents I want are the bits that flow in the branches, but they're related to these numbers. These are a mathematical construct that will help me solve the circuit. So if I define all these loop currents, and I define them all in the same sense, they're all clockwise here, I can then go through and say in this resistor, I know I3. I can say I of 3, which will be a function of t, would be I of A, because it's going in the same direction. This is a function of t, minus, in this case, it's I of C, defined in this one. And you could go around the whole circuit defining these loop currents. Okay, well, let's maybe do a couple of real examples with real circuits and see if we can apply this technique and see if we can solve a circuit. So let's have a look at one that looks similar to what we looked at last time, but I think it's got different numbers. It's going to be a voltage source, which is plus minus. This is 12 volts, connected to a resistor. Another resistor. This one's plus minus. This is 3 volts. This is 3 kilo ohms, 6 kilo ohms, and 6 kilo ohms. Okay, and we're going to use loop analysis to solve this one. Clearly that's what we're learning about. So we could define two loop currents, and again we'll define them as clockwise. And let's just call this one I of 1. And we'll go I of 2. And the question actually, because we need a question before we go further, Q, what is the current through the central resistor? So let's call that I naught, flowing down through that branch. What is I naught? Okay. Well, if we're doing loop analysis, we're going to walk around these loops and figure out voltage drops. Or we're going to follow the currents that are flowing within the loops. Now, okay, I'm moving from current to a voltage, but the conversion is easy. It's Ohm's law. So if I know the current through a branch, I can apply Ohm's law. If I know the voltage across a branch, I can apply Ohm's law. It's relatively easy to say, well, if I go around this loop, I'm going to have a voltage source here, so I know the voltage change at this point. So it's going to be 12 volts. I know the voltage drop across here because I know the loop current and I know the resistance, so I can work that into a voltage. So I can walk around the loop with the loop current, and every time I go through a resistance, I know what the voltage drop is because it's the sum of all loop currents in that branch. So let's look at the first loop. And basically, as we ride along with this current, if it goes through a resistor, there's going to be a voltage drop because we're assuming we've got a positive current that's flowing from positive to negative. So as we go through a resistor, we've got a voltage drop. As we go through this source, we've got a voltage increase. So I know this voltage increase must equal this voltage drop and this voltage drop. So if I walk around that first loop, I know that happens. Now I could have, and we talked about this last time, I could put on one side of the equations the voltage increases, and I could put on the voltage drops at the other side. The book basically makes a convention that if I go through a voltage source from negative to positive, I am going from the bottom line through this, I'll call that a negative voltage. I'll say I've got negative 12 volts. If I do that, the voltage drops must be positive. So the voltage drop due to the current flowing through this resistor must be positive, and the voltage drop going through the next resistor must be positive. And that's exactly saying voltage drops on one side, voltage increases on the other side. So whichever makes sense to you, I'm happy if you want to work with. Okay, so the voltage drop across this resistor is 6 times V equals IR, so the current is I1, resistance is 6 kiloohms. So I know the voltage drop across there is going to be 6K. So it's going to be plus 6 kiloohms times I of 1. Plus the voltage drop across this one. So again, I've got I1 flowing in the direction I'm walking around the loop, so I'm flowing with the current, so I'm sitting on an electron or a positive charge flowing around this loop, so I'm going in that direction. I go through the 6K resistor, so I'm going to have 6K, which is going to be the resistance. The voltage drop across that resistor is going to depend on this current and this current. So if they change relative to each other, voltage is going to change. Clearly the voltage drop across this resistor is this resistance times I naught, which is what I want. I need to know the current flowing through that branch. But I can see I naught is going to be I1 minus I2, because they flow in opposite directions. So that would say that the voltage across that arm would be I1 minus I2. And I know all that equals 0 because I've walked around the loop and got back to the other end. So all the potential increases, potential decreases have averaged out. So if you want to say on one side voltage increase is 12 volts and that equals all these voltage drops, you'd have the same equation. And you can see that if I just take the minus 12 to the other side. Okay, so I can rearrange that. I've got 6I1 plus another 6I1, so I've got 12,000 times I1 minus 6 I2 equals 12. And there's a K in here clearly because I'm working in kilo ohms. It's okay if you want to write 12,000 down, that's also fine. So I've come up with one equation, two unknowns in that loop. Now, if I look at the second loop, can I do the same again? Well, let's start at this bit. As I go through this first resistor, I could work out the voltage change. And the voltage change this time would be, well, I'm going clockwise. I'm going to walk from the bottom up, along, and down. So I'm going parallel to I2. So it's going to be 6 kilo ohms multiplied by, open bracket, the current I'm going with, I2, minus I1, because it's now going in the opposite direction. So that will be, we'll call equation 1. This is loop 2. And I'd say that I've got 6 kilo ohms I2 minus I1. And I'm writing voltage drops as positive because I'm going with the current. So as I go through the 3 kilo ohm resistor, I'm going to have I2 times 3 kilo ohms. That's going to be the voltage drop across that resistor. Plus 3 kilo ohms times I2. And then I'm going to have a voltage drop going through the voltage source, which would be I'm going from the positive side to the negative side, so my rule of thumb is saying if I keep all the terms on one side, I would call that positive 3. So as I go through with one of these current, that would be plus 3 volts. All that equals to 0. And that's consistent with voltage increases, voltage decreases going around the loop. If I moved the voltage sources outside of to the other side of the equation, this would become negative 3, but the current is going from the positive into the positive terminal, out of the negative terminal of this battery. So it's going from the opposite direction that I would normally expect it. If I just had a battery and one resistor, the current would come out the positive and go back round into the negative. So this is the loop current I've defined has to be flowing in the opposite sense. Okay, so if I write that down, I get, let's go over here so it's not so close to the bottom, minus 6 kilo ohms I1 plus 9 kilo ohms I2 equals minus 3. So I've got two equations. That relate I1 and I2 together. Two equations, two unknowns. You can solve those. Questions? Most of the problems we do here, it's a case of looking at the circuit, figuring out which way might be the easiest or simplest to solve the circuit. And then the tricky bit is actually coming up with equations. It's figuring out whether if I'm summing currents or adding voltages around the loop, do I sum up the currents correctly or the voltages correctly? Do I take the correct notation? Once I've done that, I've got two equations, two unknowns. I can solve that very straightforwardly. Happy? Okay. I guess the third thing we know about this, so if we look closely, I naught is what we want. So I could say from this that I naught is flowing down, so that's just going to be I1 plus I2. So if I can solve these two equations, I get I1, I2, hence I get I naught. So solving gives I1 equals 5 over 4 milliamps and I2 equals 1 over 2 milliamps. Yes. I1 minus I2, clearly. Currents are going a different way in the loop. So we'd have figured that out when I get to this stage, because I naught is I1 minus I2. And that, if I subtract a half from 5/4, I get 3 over 4 milliamps. So do you figure out how your calculators work? You forgot, you had plans for the weekend. It didn't include playing with a Casio or a Sharp calculator. Well, here's an example for you to try now. And figure out which mode buttons you have to press to bring up the window, and then you can plug these numbers in and hopefully get those numbers. So solving 2x2 equations or 3x3 equations is going to be something that should become routine, because it's going to happen again and again. Most of the circuits you look at will need you to solve those equations. As I say, the key bit is getting the equations correct, not doing the solution. If you get the equations correctly, you can now put them into your calculator and it will give you the values for the different, in this case, currents I1 and I2. Okay, questions? Okay, so that's an example of loop analysis. You could probably do this one with nodal analysis. You may be able to do it in a number of other ways. We'll talk about superposition probably later this week or next week. That would be another technique we could apply here. So on some of these circuits, there are multiple ways of solving them. It doesn't much matter unless the question says use loop analysis to solve this, and then it requires you to use loop analysis. But there's often more than one way to solve some of the simpler circuits. Once they get more complex, one technique will become more simple than the others. Okay, well, if you're happy with that, let's look at one more example. Okay, so that last one had voltage sources in. Let's look at one that's got a current source in it now. So we're going to have a current source. And a voltage source. So this is a current source. It delivers 2 milliamps. And the circuit has got a bunch of resistors in it. Call this 4K ohms. This is 2 kilo ohms. This is minus plus 2 volts. And this is 6 kilo ohms. And the question is asking you two things. Take a voltmeter across that 6 kilo ohm resistor and measure the voltage. What do I get? And what is the voltage V1 at this point relative to the same bottom line? Or what is the voltage across the 2 milliamp source? So calculate V naught or V out and V1. So again, we're looking at loop analysis today, so let's create a loop current. We'll call a loop current that way, and we'll call it I of 1, I of 2. Okay, what do I know about this circuit? Well, I know I1 in terms of a number. I1 equals 2 times 10 to the minus 3 amps, or 2 milliamps. So I've drawn a loop current. There's nothing else going through the current source except current I1 in terms of the loop current, and the current source gives me 2 milliamps, so I1 must be 2 milliamps. So when I've got current sources, I'll usually know a current in a loop somewhere. I knew one of the loop currents straight away. Okay, so loop 2. Now let's just make this V equals 0 down here, or ground it. So let's go from the ground, and we'll walk around the loop and work out the voltages. So do you want to write down the equation? So it's an exam now, an exam room here. So question is, what's the loop equation for that second loop on the right? You can debate. Well, we're going to use the same process that we've already used. We're going to walk around the loop. So let's start at the bottom where it says V equals 0 and go up that first branch in the middle through the 2 kilo ohm resistor. Voltage change would be, so I'm flowing along with I2. I'm going in the direction of I2. So the current through that resistor is going to be I2, times 2 kilo ohms will give me the voltage. I'm going through the 2 volt supply. Which way am I going? Going from the negative side to the positive side, so if I'm keeping everything on one side, I'll write that down as minus 2 volts. Voltage drop across the 6 kilo ohm resistor. I2 times 6, so there you go. That's the equation. So first bit is 2 kilo ohms times, I'm going with I2, minus I1, minus 2 volts, because I'm going from I'm going into the negative now to the positive terminal. And then I'm going to have a voltage drop, which I'll also call 6K I2 equals 0. So if I rearrange that, I get minus 2K I1 plus 8K I2 equals 2. So this one's easier to solve. I can plug one into the other and get a solution. Or I could also say that I've got 1K I1 plus 0 I2 equals 2 2 milliamps, or 2. Yeah, I have to multiply by, it's not 2 millis, I have to multiply this by 1K at each side to get this into the same units. Or if you want to write it in the same format as below, so you can plug it into this equation solver in your calculator, I'd use the one on the top right. Or I can just plug in I2 in milliamps and work out the numbers here. Okay, so if you do that, I get I2 equals 0.75 milliamps by solving those two equations. V dot, or V out, is 6 kilo ohms times I2 equals 4.5 volts. Okay, so I2 goes through this resistor. If I know the current through a resistor, I know the voltage across the resistance. So again, it's always Ohm's law in a single branch. So that was easy to work out. Finally, V1, how do we get that? So I know voltage here, I could work out the voltage here, I know current, so I could begin to work out. I could say, well, I just worked out that is 6.5, was it? No, 4.5 volts. I know I've got a voltage source here of 2 volts, so that is in the other sense, so that must be 2.5. I know the current through this resistance, so I know the voltage change here, so I can work back. So you could do that, which is equivalently what we're doing. We're walking around that outside loop, adding up all the voltages. So we could say that looking at the outside loop, well, if I go through this current source, what's the voltage change? That's a question I could debate for a while, or you could debate for a while. All you know about the current source, it delivers a certain current. If it's delivering a certain current, it must have a voltage, but you don't know what that voltage is. In this case, we've given it a name. We've called it V1. So we know that going from here to here, we've got a potential change of V1. That's what we want to calculate. So we know if I start, and I'll call it negative V1 because I know it's a voltage increase because the direction of the current. So current flows out of the top positive and into the bottom. So if the current is flowing this way, I know the voltage must be plus minus like this. If I go round a loop and I go in at the bottom through the negative terminal, I call that negative voltage, and then all the other voltages will be positive. So voltage drop through the 4 kilo ohm resistor is plus 4 kilo ohms times I1. 4K times I1. Ohm's law, V equals IR. The voltage drop through the 2 volt supply. We're going around the top loop, right around the outside now. So we go through that voltage source. We're going into the negative terminal. So, well, no, it's just -2. All right, so the other side of the board is confusing, but if I go through here, I know the voltage change. -2 in my convention, because I'm going around the loop with the current, I'm calling voltage increases negative and decreases positive, or I can write an equation with increases at one side and decreases at the other side, if that's clearer. Voltage change across the 6K resistor, well, we know that already, but it's just plus I2 times 6 kilo ohms. All that equals 0. So V1 is what I want. I've already worked out this, and I've already worked out this one. So I know what V1 is. If you plug in numbers there, you should get V1 equals 10.5 volts. So that should be 10.5 volts across that input circuit.
So what if you just do the calculation in loop 1?
You could, you know what I1 and I2 is. So as I said, there's more than one way of doing this, and here's another way that you can check. Question is, can I just use loop 1? And the answer is yes. I know I1, and I know I2. So I know this is V1. This is I1 times 4 kilo ohms, and this is I1 minus I2 times 2 kilo ohms. So plug all those numbers in, should be the same. So, yeah. Questions? Why is it minus V1? This is a current source, and I know it's producing a current in a certain direction. I've argued that my notation for working out these equations would be if I had a voltage source that was plus minus, and I was walking around the loop and going through this, and it had a voltage of Vx, let's say, I would call this minus Vx, because I'm coming in at the minus and out of the top. If I've got a voltage source that way, it's going to produce a positive current in that sense. So I must know that this is producing a positive current vertically, so it must have a polarity that looks like this. So if I'm going through this, I'm going to call this positive. It's a positive voltage, but when I make the equation, I'm calling it negative V1, because I'm effectively going in from the minus terminal, coming out of the positive terminal. So it's a voltage increase. The others would be, well, the resistors would both be a voltage decrease, and the 2 volt supply would be a voltage increase. Anything else? Yeah.
Could you explain how you got that equation for I1?
Well, this one's easy, but this one. Okay, well, if I'm going to solve this as two coupled equations, I need the second equation in the same form as this. This is in the form of kilo ohms times milliamps. I know this is milliamps. So if I'm going to convert this, so it's got I1 equals something, well, start again. The units of this thing are volts, and this is volts. The units of this are, yeah, so if I'm going to have two simultaneous equations that I add together, they both have to be in the same units. So I have to make this one into volts. So how do I make it into volts? I multiply by resistance. So I need to convert this one so that it's in the same units as this one. So I've just converted units. So either a approach works. I can either convert it to two simultaneous equations and solve it, or I can plug in milliamps into here and just work out the numbers, and it should work out. You get more comfortable as you do more of these problems. You get a bit more comfortable with units. If I've got kilo ohms resistances and V's are in volts, 1, 2, 3, 4, 5 volts, I usually end up with milliamp currents. So there's often this 10 to the 3 between, or resistances will be powers of 10 to the 3, currents will be 10 to the minus 3 in practical circuits. Okay, well, let's draw one more quickly. And this time we're going to have a resistor. And we're given a bunch of values. We're told this is 2 kilo ohms, 4 kilo ohms, 2 kilo ohms, 6 kilo ohms. This is plus minus 3 volts in that sense, and this is minus plus 6 volts in that sense. Now we take a voltmeter and we apply it across here. I don't need to write a question, it's just what is V out. Clearly this is going to be another loop of the analysis example, and just to get you started I'll say that this would be first loop, this would be the second loop. We'll call this I subscript 1, this I subscript 2. I'll leave that for you to think about before Wednesday. Can you write down the two equations for loop 1 and loop 2, and hence work out what V out is? And I guess when you learn math at high school, or even when they come here and they teach you math, what do they tell you to do? They must tell you to do something. Lots of problems, lots of practice. And unfortunately you'll see this section, of course, feels different from the first section. The first section, we were introducing new concepts of statics, electrostatics, electric fields, magnetic fields, moving charges. We're solving all sorts of equations. Here, the number of concepts are less, but the complexity of how we apply those concepts gets harder because the circuits get more and more complicated as we move forward. So this type of thing you should be able to sketch down, write down those two equations and solve very quickly. Okay, so I will see you Wednesday.